In this video I talk about parametric fitting with rational functions. This is very similar to the fitting with polynomial functions, about which I have talked in my last video. We just have to choose a different type of fit type, and I will show you in a minute how we can do that. So let's start in the script example underscore ratfit. I set a breakpoint in line 2. This is the usual preamble. Let's just have a very quick look. Setting some default, some format specifications, and some abbreviations. And I set the random number generator to its default seed of 0. So let's step out again. I will demonstrate a fit with rational functions on the example I also used with polynomials, not very successful in this case. This is not surprising because the logarithmic function, which generates the data in this example, has a pole at 0, and of course a polynomial cannot approximate this very well in the vicinity of 0. So I generate my data according to the log model. The fit interval runs from 0.5 to 5. And then we'll have a look at the approximating function in the interval from 0.05 up to 10, and we'll see how well we can extrapolate the fitted function beyond the fit range. I set sigma, the standard deviation of the Gaussian noise, to 0.1. A rational function is a quotient of two polynomials, and we can choose the degrees of the polynomial in the numerator and the degree of the polynomial in the denominator. I let both of them run from 1 to 3. I define my x values, and now let's have a look which rational models are available. I switch to my browser page. Here we are. So here we see again the library model types for curve fitting. We talked about the polynomial ones in the last video, and now we'll talk about rational functions. They are called rational polynomials in this documentation, which usage I do not recommend. It's a rational function. It's also not a rational equation. Anyway, so let's have a look which models are available. Here you see the general form of a rational function, a polynomial in the numerator and a polynomial in the denominator. Of course, this is defined uniquely only up to a constant, both in the numerator and denominator. So the convention here is that in the denominator, the highest coefficient, the coefficient of the highest power of x, is 1, and this makes the model unique. And we are allowed to specify the degrees of the polynomials between 0 and 5 in the numerator and between 1 and 5 in the denominator. So let's return to our script. Okay, generate the true model, and then I add Gaussian or normally distributed noise with mean 0 and the predefined standard deviation, 0.1 in this case, as you can see in line 11. And now I loop over all combinations of degrees, both in the numerator and in the denominator. And we will draw figures for each combination. This will give us a total of 9 figures for the fit, and then another 9 figures for the evaluation of the fit. Okay, this is just preparation of the graphical representation. Okay, now in figure 11 you see the green line, the true model, and the blue stars or pentagons are now the data, the observed data, which are noisy. They do not exactly follow the models, but they are close to it. Okay, so let's carry on. Now I define the fit type. The type string looks like this. So the model name in this list, in these library models, is RAT11, so rational, and then the degrees for numerator and denominator. So this is a quotient of 2 linear functions. Then the fit proceeds just like with the polynomial models. I can evaluate the fitted function at any point. For instance, I can evaluate the fitted model at x equals 3 with the method feval of the class myFit. I recall that myFit is of class cFit, curve fit, and it has a lot of methods. And one of them is feval. You see it in the last row of this list of methods. We will learn about some more methods in the next video. Now we can plot the fitted curve. Please note that plot, which is called here, is also a method of myFit, of the object myFit, or of the class cFit. So this plot function is different from the usual plot function we use to plot curves or points. So now we see the fitted model, the fitted rational function, as the red curve. You see the fit is quite good even with the low degrees in the numerator and the denominator. Then I plot the residuals, which are the differences between the observations, the blue stars or pentagons, from the fitted curve. I just have to get the legend right. Now you can see the residuals as the blue inverted triangle is connected by a dotted blue line. As I said last time, these residuals should be more or less random. They should not show a clear trend, and this seems to be the case here. And their absolute size is compatible with the standard deviation that I've used for generating the white noise according to a normal or Gaussian distribution. So this looks like a very good fit. And I've now put some text in the lower region of the figure where you can see the R squared, which is the coefficient of determination, or Bestimmungsmaß in German. The closer this is to 1, the better the fit. And then we see the root mean squared error, which is the sum of the squared errors divided by the number of degrees of freedom, and then taking the square root of this number. And you see that the RMSE, the random mean squared error, is quite close to the sigma I've used for generating the noise. And this shows that the model is able to follow the actual function very closely. You can see this, of course, also visually in the figure. So now, a possible problem with rational fits is that the denominator may have a 0 in the fit range, in which case the fitted function, the fitted rational function, has a pole. And this means that in the region around this pole, the fit cannot be very good, because the fitted function approaches infinity if you get closer to the 0 of the polynomial in the denominator, whereas the true function does not. So I have to check whether the polynomial in the denominator has a 0. This can be done very easily. I extract the values of the coefficients. Let's have a look what the fitted coefficients actually are. So you see the model is a quotient of two linear functions. In the denominator, the coefficient of x, which is the highest power of x here, is 1. So we have two coefficients for the numerator, p1 and p2, and one coefficient for the denominator, which is q1. So I extract all the coefficients by means of the method coef values. You also see it in the list. In the top of the command window, second row, second column, method coef values of the coefficients. And then I collect the coefficients of the denominator. The first has to be 1, and the rest I take from the vector c. Now I have the coefficients of the polynomial in the denominator, and now I can compute its roots or zeros with the function roots, which is a function in the Matlab toolbox, so it's not in an external toolbox but in the Matlab core. And now I check whether any of these roots are inside the fit window, the fit interval. This has only one root, it's a linear polynomial, and it's at minus 2 point something. So there is no problem, we have no roots in the fit interval. Okay, now we want to examine the quality of the fit also beyond the fit interval. So I have this extended interval, which I'll show you again. It runs from 0.05 up to 10. Recall that the fit interval runs from 0.5 to 5. And now I just plot the absolute and the relative error between the true function and the fitted rational function. Okay, so let's skip just the plot commands and let's go right to line 93. So on top, in the top panel, you see the relative error of the fit, And in the bottom panel, you see the absolute error. The spike in the relative error is due to the fact that the function value around 1 is very close to 0, so the absolute error can get very large. But we see at the same time that the absolute error, so the relative error, gets large around 1, but the absolute error is not very large at all. So the absolute error is a very smooth function, and of course it's not 0 everywhere, but it's not very large if we extrapolate beyond x equals 5. So let me now clear all the breakpoints, and let me continue for all the fits. We have 9 fits in total, and then let's check whether we can identify which one is the best one. So this is RAT 1,3, degree 1 in the numerator, degree 3 in the denominator. Now we step up the degrees, both numerator and denominator. This is interesting. This is a fit with RAT 3,2. So we have a cubic polynomial in the numerator, a quadratic polynomial in the denominator, and obviously this polynomial in the denominator has a root inside the fit range. It's at 0.7 about, and you see the spikes in this function here is a pole of the fitted function, and this disqualifies the fit because around this pole the approximation of the fitted function to the true function cannot be acceptable. This problem gets more severe if the degree in the denominator increases, because you know that the number of zeros, maximum number of zeros, is just this degree. So if you have a polynomial of very high degree in the denominator, there is a good chance there will be a pole inside the fit range. So we have now finished with all fits, and at the end of the script I extract all the RMSE values and all the R² values. I have stored these structures, myGov, and the objects myFit in an array and a cell array, and now I can extract all these fields in the following way. If you look at line 97, I store all the fields RMSE in the structure myGov. Gov is goodness of fit, I recall, in the vector all RMSE. You have to put a square brackets around this expression, otherwise this will give not a vector but a lot of scalar results. And the same for the R². Now we can compare the fits in the command window. You see that the RMSE is almost identical across all fits. It even increases with higher degrees. And the R², which should be as close to 1 as possible, is almost identical too. It's about 0.973 or 974. in most cases. So in this case, I would actually prefer the fit with the lowest possible degree. So already RAT11 gives a very good fit to the logarithmic function, much better than a polynomial fit can do in this fit interval. Of course, in fit intervals which are far from zero, a fit with a polynomial is perfectly acceptable. This terminates this video. In the next one, I will talk about general or custom models which are defined by the user.